Radioactivity. Okay, now some elements have unstable isotopes since we were discussing the same thing for carbon 14 and tritium and hydrogen in the previous pages. So yeah, tritium and carbon 14 are those examples. Now, the extra neutrons in their nuclei cause them to disintegrate. Disintegrate means breakdown. They decay, and that happens spontaneously, all by itself. You're not going to push anything. You're not going to change any conditions. You do not have to pressurize them. You do not have to increase the temperature. You do not have to do anything. It's all going to happen on its own. This is radioactivity. Radioactivity is actually nuclear fission. In physics, in your last chapters, you're going to study that fission, the specific word nuclear fission means breakdown of nucleus. All right. So when breakdown of nucleus occurs, what happens that there are particles inside the nucleus, then they are free to move out. So we have disintegrations, we have the whole breakdown. It releases a lot of energy. It releases radioactive radiation. Radiation means they might release alpha particles, they might release beta particles, they might release gamma radiations, they might release neutrons, they might release protons or electrons, they might release any of these either particles or forms of energy. So that's possible. We don't exactly go through all of this in chemistry. This is not a part of chemistry. But since some of these are studied in physics, that's why I told you that. So moving on, uranium 235 is a radioactive isotope, and this can be a very good example. This is a controlled source of forming energy in nuclear power stations. About less than a little more than 10 countries are doing that around the world. I guess around 16 different countries are capable of producing electricity through nuclear power stations around the world. Pakistan is fortunately one of them. So the decay is a completely random process. It's unaffected by temperature. It's unaffected whether the isotope is a part of a compound or present as a free element. And specifically, radioactive decay is a nuclear process. It's not a chemical reaction. Now remember, if I use the word chemical reaction, that means I'm talking about the changes through electrons. This is pretty much covered in our next chapter, the bonding chapter, where we discuss that elements sometimes lose electrons or they gain electrons or they share electrons to bond among themselves, right? Nuclear process is different. Nuclear process is actually based upon fission. At fission means the nucleus is going to break down. It might release any kind of subatomic particles or other particles or different forms of energy. So radioactive decay is going to be a nuclear process. It's not going to be a chemical reaction. There is a big difference right there. Okay. Uses of radioactivity. First one, radioactive dating. Now, every radioactive isotope decays at its own rate. We have a specific definition, half-life. The time taken for a radioactivity sample to half its constant at a particular radioisotope, this time is known as half-life. Usually we do it by mass. For example, we have 1 gram of U-35 present. After some time, it's gonna decay, and when we exactly have zero point 0.5 grams of U-35 remaining, the time taken for this to happen, all right, that time would be known as half-life. Life for it to be half about its constant. So some isotopes have very short half-lives, only a few seconds. For example, oxygen 14 is a radioactive isotope. It has a half-life of 71 seconds. 71 seconds, half of its mass is gone. Another 71 seconds, another half of it's gone. So other half-lives are quite long. Carbon 14, on the other hand, is 5,730 years. The example of uranium, this one, you'll be amazed to know that's around 710 million years. Million years, not just years. 710 million years for an isotope to come to half of its mass. So some half-lives are really long, some half-lives are really short. We're going to discuss about francium. The half-life would be even shorter than 71 seconds. That's actually in the next chapter. So one important use of half-life, radiocarbon dating. Now, since all life is made up of carbon, That carbon can be carbon 12 or but a little part of it is carbon 13. A very rare and small portion of it is carbon 14. And we can use that carbon 14 to date wooden or organic objects, maybe remains of plants, maybe remains of bodies, and we can actually date it. That's how we were able to date mummies. Now we can easily say this mummy is this many thousand of years old. Now how come the scientist is able to say that the mummy is this many years old? Or how come we were able to say about something about dinosaurs? We can say dinosaurs were lived at the same planet for about this many years ago. How come we are able to say that? Radioactive dating or radiocarbon dating is actually the way to do that. We have remains of those dinosaurs, and out of those remains, we have a few isotopes of carbon 14, which actually gave us the idea that how many years ago were they present in the living form on the same planet. Make sense?
Yes, sir.
Great. So industrial uses, well, uranium-235 is used in nuclear power stations, and we safely produce a lot of electricity with that. We actually bombard these atoms with neutrons. Huge amount of energy is produced. We do the same thing in atomic bombs. The difference is that nuclear power station, the whole thing is controlled. We don't let it explode. We do the whole reaction in a much controlled, cooled way. Other industrial uses are pretty easy. The diagrams can explain that. For example, we have big liquid containers in industry, 50,000 tons, 100,000 tons. When we are filling those in, not a single person can stand and monitor it. What do? We have radioactive sources, we have detectors, and we can always check the level of filling in of those containers. Second use, if we have gas pipelines and we have a crack in them, now gas pipelines go around hundreds and thousands of kilometers around the country. Now, how would we know at a specific place we have a leak? Now, we can actually trace it with a radioactive tracer. Along this with the gas, it would be leaked from a specific place, and we can always detect it. Third and last use in this case is that the metal sheets or other kinds of sheets, when we are supposed to check the thickness or thinness of that sheet, we can always come up with a radioactive source and a detector on one end, and we would definitely know how much is the thickness or thinness. Because after the specific thickness, the radioactive source won't be able to be detected by the detector. So we would know, right? These are as simple as these are. So I think we can move ahead. We can safely move ahead to medical and food safety uses. Can we?
Yes, sir.
Great. So when it comes to medical usages, though radiation on a living cell is very dangerous, biological cells are sensitive to radioactive emissions. Cells grow and divide in a particular manner, but when they observe any radiation, they experience it, they become damaged. Damaged cells are also known as cancer cells. Cancer cells grow in out of control manner in the body. They form entire tissues and entire masses in the body if they are not controlled properly. But since radioactivity can kill cells, so we can target those cancer cells and kill them by radiation. We can do it in such a way that we keep the healthy cells living and we only target the cancer cells. So, penetrating gamma radiation from radioactive isotopes such as cobalt 60 is used to treat internal cancer tumors. Skin cancer tumors can be treated with less penetrating radiation, such as radiation by phosphorus 32 or strontium 90 isotopes. This is done by strapping sheets that contains these isotopes on the affected area of skin. That's how we treat skin cancers. So that's a very good way. Radioactivity can help us detect cancers. Not just that, it can also help us kill cancer cells, get rid of cancer. That is commonly known as chemotherapy, right? Moving on, bacteria cells grow and divide rapidly. They are particularly sensitive to radiation. So the medical instruments that are commonly used in operations, dressings, syringes, we can sterilize them. Sterilize means to kill all germs on them. Previously, this was done right on top of a flame, but now we can sterilize them by sealing them in polythene bags. We expose them to intense doses of gamma radiation. This can kill all kinds of bacterial cells. So now we know that the syringe or a dressing or any specific medical instrument that we're going to use before an operation is completely sterilized. This is a very effective method to kill all the bacteria, right? So now we know many usages of radioactivity. Moving on, we have a very small topic that we uh, can quickly cover: electron arrangement. Now, we already understand that the center of an atom is known as nucleus, and nucleus actually holds both the protons and the neutrons. When it comes to electrons, they actually revolve in different levels or shells around the atom. All right. So the shell that is closest to the
Yes.
nucleus is known as the first shell. However, shell was an old word. The oldest word was orbit. It was actually taken from our whole planetary system, the solar system. We don't use that word anymore. Then we kept on using the word shell. We still do. However, much better word would be energy level. Since these circles hidden, you can see have a specific energy. The first or the lowest energy level is the one that is closest to the nucleus. This is so small it can only hold two electrons. No more electrons can fit into it. The second one is one which is a little farther away from the first one and the nucleus. Actually, it can fit more electrons, but the maximum it can fit are 8. Third in energy level is the farther one than the first one or the second one. This one is third, this one's second, this one's first. That's how they are numbered. So that's pretty easy. You can keep numbering on the shells as farther you go from the nucleus. So the third energy level can actually fit in 18 electrons, but it becomes stable at 8 electrons. Stable means that's good enough and we can start filling on the next one. All right. So this is the
Yes.
maximum number of electrons it can hold. These are the number of electrons on which it becomes stable. These are the number of electrons the second shell can hold and become stable, and that's the maximum of it. These are the number of electrons which it can hold or maximum of it. So for the third shell and onward, yeah, they can hold more electrons, but they become stable at 8. That is something we need for the student to remember at this point, although this doesn't make much sense, but that's about it. We're drawing actually a boundary line over here, since more explanation would come in advanced levels and not at this level. Now, for this entire circles that we were going through, and I was going with an explanation, were actually explained by Bohr's theory. Bohr was a scientist. So let's go with a simplified version of it. Number one, electrons orbit around the central nucleus of an atom. Easy. We have just discussed that. Now, those electron orbits are called shells. Better yet, you can make all them energy levels since they have different energies. Now, shells which are further from the nucleus have higher energy. The shell which is closest to the nucleus has the lowest energy, and we start filling in the electrons with that shell. So the first shell can only hold 2 electrons. The second and subsequent shells can hold more electrons, but at 8 electrons, they actually give a stable or a noble gas arrangement. Stable means the arrangement of the nearest noble gas or the arrangement at which we can start filling in the next shell. Now, where we have a huge table on the next page, from this table, you're going to get an idea that the first shell is always completed at 2 electrons. So if you have more electrons like you do in other elements after hydrogen or helium, we have elements that have high atomic numbers, so definitely they have more electrons. So we start filling in the second shell. First electrons, two, three, four, five, six, seven, eight. After it, you'd notice that we stop filling the second shell and we start putting electrons in the third shell. For example, take a look at sodium. There you have sodium, the symbol Na. We have 11 electrons. So yeah, we put 2 electrons in the first shell, we put 8 electrons in the second shell, then we can't put any more in the first and the second shell. So we have to put the third electron in the third shell. And that's the way we write it. We write the number of electrons in the first shell, comma, number of electrons in the second shell, comma, number of electrons in the third shell, comma, number of electrons in fourth, fifth, sixth, so on and so forth. All right. So we keep on writing that. You'd notice that for the first 20 elements, this table has been filled for you. Interestingly, for potassium number 19 or calcium number 20, this is 2882, which means we only put 8 electrons in the third shell and then we start filling the fourth one, even though the shell can hold more electrons. This is so far we come in O level. So what is the purpose? We are actually drawing a boundary line. We're not explaining any more at this level. We'll definitely explain why this happens in the upcoming advanced level. So that's how we can draw carbon atom. So it has six protons and six neutrons, and it has six electrons, two of which belong to the first or the closest shell, and the rest of the four belong to the second shell. Make sense?
Yes.
In a similar way, we can always writing the electronic configuration is done like this. These numbers 2, 8, 1 or 2, 8, 5, something like that. This is how you write the electronic configuration. If you are given with the word state, mention, write the electronic configuration, you're supposed to do it like this. All right. But as soon as they use the word draw, the electronic configuration or draw, then this word means this, these structures. For the nucleus right in between, then the first shell, second shell, third shell, so on and so forth. For lithium, it's going 2-1 turns to this, or 281 means this, or 2881 means this. Now, here
Okay.
I want you to notice one more thing. This is 2-1. Add these numbers. This is the proton number of lithium. This is 281. 2 plus 8, 10, 10 plus 1, 11. This is the proton number of this element. 2 plus 8 plus 8 plus 1, 2 plus 8, 10, 10 plus 8, 18, 18 plus 1, 19. That's the proton number of this element. So if you add all of these numbers, all right, what are you going to end up with? You're going to end up with Z, or proton number of that specific element. So you can work your way out. From 19, you can get these numbers. From these numbers, add them up, you can get 19, the atomic number. That's how you can always track this. Make sense?
Yes. Yes.
As soon as we're gonna start the next chapter, we're gonna tell you two more important pieces of information, which I'm gonna tell you right away. You're familiar with groups and periods in periodic table. The horizontal line in periodic tables are periods. The vertical columns in the periodic table are known as groups. Now, if I write this number like this, 2, 8, 8, 1, you can may use dots or you may use commas, but no the symbols. The dashes, the slashes are not kind. So I ask my students to prefer comma over dots, since that's easier to put and you can keep the difference between the decimals and these numbers, right? But make sure you don't
Yes.
use any other symbol except a comma or a dot, all right? So when we write these numbers, let me tell you, 1, 2, 3, 4, since there are four numbers, so it's fourth period, all right? And the last one depicts it is group 1. And 2 plus 8 plus 8 plus 1 is equal to 19, which actually depicts its atomic number Z. So these are the pieces of information which have been done for the periodic table in a very careful manner. Periodic table is not just a table in which we combine all the elements in a random manner and there you go, we have a table. Now you can brag about it. No, it's not like that. It has been worked upon for hundreds of years, and a lot of scientists have actually put a lot of effort into it. So there are many things about the periodic table that are very good, and the data can be extracted from the periodic table. And many pieces of information can be extracted from the periodic table. To begin with, period number and group number or the atomic number can always relate and work with electronic configuration. All right.
Yes.
So if in the exam the examiner comes up with some weird set of numbers, Don't worry. For example, he comes up with 2, 8, 18, 18, 8, 1. Now that's a weird set of numbers. Not familiar with it. But 1 means it's group 1. These are 5 numbers in total. So that means this period, right? And if you add up
Yes.
2 plus 8 plus 18 plus 8 plus 1, you are also gonna get Z of it. You can exactly locate what the element is or where it lies in the periodic table. No matter how confusing or scary configuration he can come up with, do not worry. Let me tell you, first shell can hold a maximum of 2 electrons, second can hold a maximum of 8 electrons, third may become stable at 8, but it can actually hold a maximum of 18. Fourth and every subsequent shell can hold a maximum of 32 electrons. So they can hold more. Yeah, we may have some skinny numbers over here. We may have 18 or 32 or any number in between over here, but that doesn't mean you can't find out the group or the period or the atomic number of that specific element. So never worry, no matter how scary the numbers are. You can always know these 3 specific things.
Yes.
Are we good?
Yes, sir.
Great, great. Any more questions?
No, sir, it's clear.